everyone. Today we are going to learn about electronic displacement effect. This is basically part of general organic chemistry. Here, so after some time, we will learn about inductive effect and resonance effect. But before that, we need to learn some basic things like how in organic reaction bond cleaves. First, we will see bond cleavage. We know that in any organic reaction there is some bond breaking and bond formation. Like in any organic reaction there is some reactant and product. What happens in the organic reaction? In presence of some reagent, uh, substrate reacts with reagent to give some product. Bond breaks in reactant and bonds are formed in product. There are two types of bond cleavages. Before that, how bond cleaves we should learn. Like what happens, let's suppose we have any carbon and hydrogen bond and other groups are attached here. We need to break this CH bond. Then how we can break it? Like here we know there is two electrons between these bonds. This is a covalent bond. So there is sharing of electron between this carbon and hydrogen. There are two electrons between in this sigma bond. What happens? There are two orbitals. There are two orbitals. This is sigma and sigma star. In our case here, we have two electrons in our sigma bond, which we can show like this. If we want to break this bond, what we can do? We need to transfer some electron in say sigma star orbital, so that the bonding and anti-bonding orbital electrons cancel and our bond breaks. This is some basic thing. Let's leave this for right now. But how we can break this bond? In two ways we can break this bond. Those two ways are like first is homolytic fission. What happens in homolytic fission? Let's suppose there is a bond between A and B atom. In homolytic fission, if we have a bond between atom A and B, then there are two electrons between this bond. These are shared between these two atoms. But in homolytic fission, what happens? This electron is taken by this atom, and this electron is taken by this atom, and they break to form A, B. These two are radicals. I am representing this with dot. It means that the electrons shared by this A atom in this bond is taken by its atom A, and by electron of shared by atom B is taken by atom B to form these free radicals. Please note that this half-headed arrow, whenever we need to transfer one electron to the atom, then we should use half-headed arrow, not a full-headed arrow like this. We should note this thing. This is one part. Very soon we will learn about these free radicals, but before we should learn some basic things. Second thing is heterolytic fission. In a heterolytic fission, let's suppose we have a bond between A and B. In this case, we had two atoms in which the electronegativity difference was very less. But now in a heterolytic fission case, the electronegativity difference between A and B is more. Like we have some carbon and oxygen, so bond between carbon and oxygen, something like that. For now, we are taking it as A and B atom. What happens in homolytic fission? Like suppose electronegativity of atom B is more than atom A, then what happens? Both the electrons shared between these two atoms are now taken by only B atom. Now we will show with double-headed arrow. It means that both the electrons are going to atom B. Now it will result in the formation of a positively charged atom, and we should not say atom like there in organic compound, like we have methane say, then we have then there will be formation of carbocation like C, CH3 plus. Then it is not accurate to say atom. Okay, we should know this thing. Now the other thing will be carbon anion. So in homolytic fission, there will be formation of radicals. In heterolytic fission, there will be formation of carbocation and carbanion. This is positively charged species called carbocation, negatively charged species called carbanion. Very soon we will learn about these things. Reactive intermediates, like in any reaction, there is reactant and product, but during the formation of product from reactant, there are some intermediates, reactive intermediates, which forms between the reaction, which is not obtained in final product, but it takes parts in the reaction mixture. We will see them now. Now we will learn about reactive intermediates. The in in our level, we have to learn only about three reactive intermediates, but there are some other reactive intermediates also. But about them we will learn in our highest classes. For now, the especially three reactive intermediates are important for us. First one is carbocation. Ca- we know about carbocation. Any positively species is called cation. When we use carbo, it means the positive charge, carbon. Like we have, let's say, we have methanol. We have methanol. There is electronegativity difference between this carbon and oxygen. Then what will happen in presence of, let's say, some acid? This will change into hydronium ion. Uh, this oxygen will attack this H plus ion to form OH2 plus. Then it will leave like this to form methyl cation. We can call it carbocation because the positive charge is on carbon. Like we should then what is the properties of any carbocation? What is the structure? What is the geometry here? What happens? Uh, Basically, the structure of carbocation is like the planar structure in which the carbon is this is the structure of carbocation in which there are six bond pair electrons, like two in this bond, two here, two here. Total six bonding pair electrons, and one vacant p orbital is there. This p orbital, and the hybridization of this carbon is sp2, like planar structure. Plenary structure means like the structure of carbocation is like this. Like carbon is in carbon, and all the three hydrogens are in plane, and p orbital is like this. One lobe is above, one lobe is below. The in our SN1 reaction, we know carbocation is formed. Many of you may know about SN1 reaction. What happens there? Due to this planar structure of carbocation, there is a racemization in the product. Like in a nucleophile can attack from below and above also. That's why we get two products. Like there is only change in the absolute configuration. Like one is R configuration and other is S. That's due to the planarity of the carbocation. Oh, next we will learn about carbanion. Now we will talk about anion. Carboanion means negative charge present on carbon atom. Let's suppose we have any. I don't know. Many of you may know about Grignard region. What happens in Grignard region? You might have seen this R and GX written in the books. This is nothing but Grignard region. We are talking about methyl magnesium. Let's say methyl magnesium bromide, that is CH3 Mg X. We are talking about methyl magnesium, like X is nothing but halogen. Let's suppose we have bromide here. What happens, like let's say we have this type of structure we have. What happens here? This magnesium is less electronegative than carbon. Then what was happening in carbocation case? We had carbon and oxygen bond. Then oxygen was more electronegative than carbon. That's why the shared electron was going towards oxygen like this. But here, what happens? The electronegativity of carbon is more than magnesium. In this case, this carbon is going to be negatively charged after taking the shared electron between these. Then what we will get? We will get minus, something like this. This is carbonion, methyl carbonion. The negative charge is present on our carbon atom. Then what is the properties of this carbonion? The structure of carbonion is like this. Like these two electrons have negative charges present here, and the hybridization of carbon here is sp3, and the structure is shape is pyramidal. Carbocation was planar, but the carbonion is pyramidal in shape. Next is free radical. What happens here? Let's suppose we have a bond between carbon and carbon. Let's suppose we have ethane here. These free radical reactions are mainly happen in the presence of light. In presence of photons, these bond breaks, and these electrons are gone to these carbon atoms to form species like this. These are not charged species, because they are retaining their own electron. Like this one electron shared in this bond, but these two carbon atoms shared their one electron. Now they again have their electron separately. Then for properties of free radical is that this is also planar, like carbocation, like this. sp2 hybridized, but now this carbocation in p orbital of this methyl radical, we have one electron here. In carbocation case, this p orbital was vacant, but now we have one electron here. And this is sp2 hybridized planar structure. Then these are three important reactive intermediates from our aspect, but there are two more reactive intermediates like nitrene. We have structure is like any R group attached to nitrogen, like this. These reactive intermediates are formed in reaction like Hoffman reaction, Curtius rearrangement reaction, but we are not concerned about these reactive intermediates now. And one other is carbene. Like this is like the structure is like this. This reactive intermediate is mainly formed in the name reaction, which we know that is called Riemann-Tiemann reaction. In that particular reaction, these intermediates are formed. But we are not, these two reactive intermediates are not important for our level. It is taught in higher classes. Next thing, we will go to our important today's topic, that is inductive effect and resonance effect. Let's start now. Now we will learn about our important topic, that is electronic displacement effect. It is mainly of two types, like permanent and temporary. Permanent means this is always present in the molecule, like we have methanol there, then this effect will be always present there, or any other molecule also. Temporary means that this effect will be this effect will come into action only in the presence of some region, some outer region. We will learn about this now. Before that, permanent effect. First is this is of three types mainly: inductive effect, mesomeric effect, hyperconjugation effect. This mesomeric effect is also sometimes called resonance effect, but there is very small difference between mesomeric and resonance. Mesomeric is directional and resonance non-directional. We will learn about these things. What is inductive effect? This inductive effect is mainly seen in any saturated compounds, like there is only sigma bonds present there, like we have methyl iodide, say, let's say. Now this is electronegative atom, we know, and this carbon, it is attached to carbon. What happens due to electronegativity property of iodine? What happens? The electron between these bonds is more pulled toward this electronegative atom, like toward this atom, and this is operating through sigma bond only. That's why it is. I said that this is mainly applicable in saturated compounds. Then this inductive effect is represented by the symbol I. This is of two types, plus I and minus I. Oh, what is the meaning of plus I and minus I? Plus I means that the electron from the any group is pushed from the group, like we have any, let's say we have CH3 group here, CH2 and CH3. Just focus on this methyl group. This carbon is not much electronegative. What happens if we have any, let's say, electron species here? Let's say we have carbocation here. What happened? This CH3 group will push electron toward this carbocation like this. It means plus I. This group is pushing electron towards electron deficient species. This effect is called plus I effect. What happens in my minus I? Let's suppose we have CH3, CH2, or let's suppose chlorine. What happens here? Chlorine is electronegative atom, but now it will push, it will pull electron towards itself, and we will show the arrow like this. It means electrons are moving towards chlorine. And also this inductive effect is distance dependent. Distance dependent means after like here 1, 2, and let's suppose we have one more carbon atom here, then this inductive effect will diminish after some carbon, like it is measurable only up to 3 or 4 carbon atom. That's why it is distance dependent. uh, I will write some groups which show plus I and minus I. Some important groups which show minus I effect are like NF3 plus we have here chlorine, fluorine, aldehyde group, nitro group, and etc. And plus I effect showing groups are mainly like this. We have methyl, any alkyl group, and this O minus negatively charged oxygen also shows plus I effect. Then you might be wondering why electronegative atom is showing plus I effect. I will just explain briefly. Now we are done with inductive effect. Very soon we will see some examples. For right now, I will explain these things. Then I will give examples. So the second one is mesomeric effect. What happens in mesomeric effect? For mesomeric effect, there it is present in pi bond containing atoms, molecules. Like we have some alkene. Let's say we have some other atom here. Let's say another pi bond present here. What happens in this? Let's say we have nitro group here. What happens in mesomeric effect? In the presence of some pi bond, and if pi bond is here, then pi star orbital is also there. What happens? This, due to the electron withdrawing nature of this nitro group, these pi bonds will delocalize in this orbital like this. Like this bond will move like this, and this will move like this. In the presence of the pi bond, this type of movement happens. Then it will result in the formation of O minus. These type of species will form. Basically, in mesomeric effect, there is the necessity for the presence of this pi bond. There is one case in which, in absence of pi bond, also this mesomeric effect is present. There are so many things in this effect, but due to a boundation of time, I am explaining it very briefly. Other thing like I will just briefly discuss what are the different cases in which this mesomeric effect occurs. There are basically 6 cases. First case is, now we will learn about 6 cases in which case mesomeric effect can happen. The first case is, we have a pi bond adjacent to a carbon atom. What happens here? Like this will go like this, and this will move like this. Then mesomeric effect can happen in this case. Second case is, we have this pi orbital is still there. Now in place of carbon ion, we have some lone pair containing species here. In this case also, this lone pair will move like this. This will go like this. This is slightly unfavorable to electron go like this, because this is more electronegative. But in presence of pi orbital here, this electron can move like this. And the third case we have here is, if we have one another pi orbital present here. Here also it can go, it can move, electron can move like this. This is the third case. Fourth case is, we have some carbocation here. We have some carbocation here. Now we have vacant orbital or vacant p orbital here. Then pi electron can move into this vacant orbital. This is our fourth case. Fifth case is, we can have one radical here. Let's say we have p orbital and we have radical. is also electron deficient, then this pi electron can move into this p vacant p orbital. And the next last, that was the fifth case. Now last and final case is, now in absence of pi bond also this mesomeric effect can happen. That last case is, let's say we have some carbocation here, we have vacant orbital, positively charged species. Now we have lone pair here, we have vacant p orbital. In this case also, this lone pair can go into this p orbital to stabilize this electron deficient species. These are 6 cases in mesomeric effect. This mesomeric effect is of 2 types. It is shown by plus m and minus m. What happens in plus m? In plus m effect, any group attached to the pi bond skeleton will donate the electron pair in the pi system. Let's say we have this. Let's say we have NH2. This is lone pair containing species. Now it will give the electron in the pi orbital like this. Then this bond will break and one double bond will form here with positive charge on nitrogen. This is plus m. Like this group is pushing the electron density in the pi electron system. Second one, this is plus m. Second one is minus m. Let's suppose we have a group like this nitro group. In this group, in this case, minus m effect case, this nitro group is electron withdrawing. It will withdraw the electron from the this pi orbital, this pi bond. It it will move like this, minus m. Like electron density is moving from the pi skeleton system to the attached group. It means this group will show minus I effect. That's minus that is minus m effect. That's all for my plus m and minus m. Now we will learn about hyperconjugation effect. This effect is also called no bond resonance. We will see why. There are mainly 3 cases in hyperconjugation. In hyperconjugation, only when at alpha carbon we have at least one hydrogen, then only hyperconjugation can happen. Here, what is alpha carbon? Let's suppose we are considering this group, then carbon attached just adjacent to this group is called alpha carbon. This is alpha, then beta, gamma, other things are also there. But in hyperconjugation, only alpha carbon matters most. There are 3 cases in which hyperconjugation can happen. This is, let's suppose we have a free radical here. This is also electron deficient species. What can happen? What will happen here? This sigma bond. This is electron rich. We have 2 electron here. This is electron deficient species, and here also this is electron deficient species. In alpha carbon we have 3 hydrogens. Here also we should satisfy that valency. Or here also we have alpha carbon 3 hydrogens. Now in pi bond, what will happen? This hydrogen will break like this, and this will break like this. Then there will be formation of double bond here as a single bond here. Then in such cases, hyperconjugation will take place. What are there are that's all for this permanent effect. For temporary effect, we will learn later. This is basically is present in our presence of some outer regions, like we have a hydroxide, base, or acids. Only this will come into play. For right now, we are doing up to here only.